So hello and welcome back for the final example in lecture 9.1 on power factor correction. So example 4, a single phase load with an applied voltage of 11,314 cosine omega t plus 14.5 degrees and a load current of 2298 cosine omega t minus 8.1 degrees is connected across a 60 Hertz power system. Find the RMS voltage and express it in phasor form with the angle in degrees. Remember, when we do our power calculations, it's a lot easier for everything to be written in RMS form. So what you're going to have here is that the phasor voltage is going to be 11,314 divided by the square root of 2, and it's going to have an angle of 14.5 degrees. So another way to write that is 8 with an angle of 14.5 degrees, and that's in kilovolts. And then for B as a phasor, you're going to have I equals 2298 divided by the square root of 2. And remember, this is RMS. 2298 divided by the square root of 2 with an angle of negative 8.1 degrees. So that can be written as 1.625 with an angle of negative 8.1 degrees. And that's going to be in kiloamps RMS. Okay, so now if we draw our power triangle, we know the voltage, we know the current, so we can use those to find our S. So what we're going to have here is S equals V I conjugate, which is 13 with an angle of 22.6 degrees, and that's megavolt amperes, or in complex form, 12 plus J5 megavolt amperes. So that means that the apparent power is 13 megavolt amperes. The real part is our power, so that's 12 megawatts, and the imaginary part is our Q, so that is 5 megavar. And then we also have the power factor angle. The power factor angle is 22.6 degrees. So we now can get that our original power factor is the cosine of 22.6 degrees. So the original power factor is 0.9. Okay, let's go on to part D. So for part D, we want to find our capacitor so that our power factor is now 0.98. So that means theta nu equals the arc cosine of 0.98. So our nu theta is 11.478 degrees. So from that, we can find Q and S. So how we do that is we're going to use that P is equal to S nu times the cosine of theta nu. So it means that S nu is P over the cosine of theta nu, or P over 0.98. So we get that S nu is equal to 12.245 megavolt amperes. And Q nu is equal to S nu times the sine of 11.478 degrees. So Q nu is equal to 2.437 mvar. Okay, so we now have our new power triangle here, where we have an angle of 11.478 degrees. P is still 12 megawatts, and our new Q is 2.437 megavar, so that's Q nu, and S nu is 12.245 megavolt amperes. And so, if we want to find our new Q for QC, QC is going to be Q minus Q new. Q minus Q new. So it's going to be 5 meg minus 2.437 meg. So QC is 2.563 megavar. And C is going to equal QC over omega VRMS squared. So QC is going to be 2.563 meg over 2 pi, and we had 60. And our voltage was 8,000. So that's going to be 8,000 squared. So the capacitor is 106.2 microfarads. Okay. So to finish, we are going to draw our before and after power triangles, our before and after phasor diagram, and that will conclude our introduction to power factor correction. So we're going to have our triangle here. Okay, and remember the whole thing is Q again, where Q is 5 mvar. Okay, QC is here, the part we subtract off. That's 2.563 mvar. And here is the original Q, or the new Q, Q new, which is 2.437 mvar. And then here are our angles before and after. So we have 22.6 degrees. And then right here, 11.478 degrees. And remember, for both, the power remains the same. So for both of these, the power is still 12 megawatts. And our S, after power factor correction, is now going to be 12.245 MVA. And our original S was 13 MVA. Okay, so now let's take a look and see what this looks like with our phasor diagram. So here we have the real axis. Here we have the imaginary axis. And so remember, we find the original load by using S over V conjugate. So for the original load, S over V conjugate gives us 1625 with an angle of -8 degrees. And this may be one of those times where it would be helpful to actually show the voltage so that you can see why it's -8. Okay, so this is 1625 and this is -8 degrees. But remember, at the beginning, we had a voltage source that was 8,000 with an angle of 14.5 degrees. Okay. So what I want you to notice is that our original power factor angle was 22.6, a little bit of rounding. And so the difference between that voltage and that current is the 22.6. So that's why it's an 8 here, because 14.5 plus 8 gives us the 22.6. So then what happens next is we find the current through the capacitor. And the current through the capacitor is the voltage divided by the impedance of the capacitor. And the current through the capacitor ends up being 320 with an angle of 104.5 degrees. And so it's not 90 anymore because that voltage source has an angle other than 0. So this is 104.5 degrees. And so it's going to go up a little bit off to the side like that. And this is the current through the capacitor. And that current through the capacitor has a length of 320 amps. And so now, when we have IL plus IC, we get IS. See if we can get a little bit more room on here. It's not cooperating with me, so I'm going to have to try this. So IS equals IL plus IC. And by doing that, so finally we get that IS equals IL plus IC. And IS is equal to 1530 with an angle of 3 degrees in amps. So it's just a little bit up like this. And this is IS, that is 1530 with an angle of 3 degrees. And I want you to notice that when this is 3 degrees with respect to the voltage, that makes an angle of 11. And that would be the new power factor angle. So this concludes our discussion of power factor correction. Please come back for more.